this one. Okay, so this week we'll be talking about conditional random fields. First, a few announcements. Homework 5 will be released later tonight. It will be due in 2 weeks. So the policy of this course is there's at most one thing due a week. The casual competition is due next week. So homework 5 will be due in 2 weeks. And if you're planning ahead, for this course, there's actually nothing due the week of the 23rd. And then there'll be one thing due each week thereafter. With regards to the homework 5, it will be about conditional random fields. Strongly encourage that you use the skeleton code that will be available on Moodle. You don't have to, of course, but I think it makes things a lot easier. And regarding the Caltech competition, the competition closes next Tuesday, and then we'll announce a winner in class. And there'll be a short report documenting what you guys did, the methods you tried, how you did validation, so on and so forth. And I cannot emphasize enough that this should be a short report due via Moodle on the Thursday.
What is your concept of short?
Just so we know. Yeah, I'm thinking like 5-ish pages plus some plots. So that's my idea of short. So like in terms of text, like 3 pages of text. Right? So that should be enough to document sort of what method you tried, the range of hyperparameters, and so on and so forth. Right? If you choose to submit a 20-page write-up, it better be really, really, really well written, or I'm going to take points out for being too. Okay. So today we'll first do a brief recap of sequence prediction. And then we'll jump into the conditional random fields, which you can think of as a sequential version of logistic regression. Analogous to how hidden Markov models is a sequential version of naive Bayes. Another way to think about conditional random fields is that it's a discriminative sequential model that learns to optimize the probability over output sequences given input sequences rather than a generative model like hidden Markov models. And we'll talk about each of these points throughout this lecture. So just a recap of sequence prediction. We have a sequence of inputs, a sequence of outputs, and for this lecture, we'll only be looking at the supervised learning case. So in the training data, you get both x's and y's, and the x's are the inputs and the y's are the outputs that you want to predict. Right? So in the previous lecture, we talked about a range of issues. In the previous week, we talked about a range of issues that are more flexible types of questions you can ask by generative models, and also unsupervised learning scenarios where you only get the x's as training and not y's. For this week, we're only looking at the supervised learning scenario where you get both x's and y's as training, and y's are what you only need to care about predicting. Okay. So a sequence of tokens, you can think of this as words, right? Inputs as words, and the outputs as part of speech tags, like in the previous week. Right? And so just an example, suppose we had 6 part of speech tags, then for an input sequence of fish sleep, the label is noun verb. For the input sequence of dog and homework, the input sequence is determine noun verb, determine noun. The fox jump, if this input was the fox jump over the fence, the output sequence would be determiner, noun, verb, preposition, and determiner noun. Right? So this is the sequence prediction problem. Okay. So as we talked about last week, we could naively think of each possible output sequence as a separate classification task, or separate class, and then train a multi-class prediction problem, which basically scores over all possible length M sequences as a different class. Right? So each of these would be considered a different class. Right? And this leads to essentially an exponential number of classes in the length of the sequence, which is in general intractable for even moderately long sequences that we want to predict on. And it's even much worse when the number of part of speech tags or whatever your output sequence state space is much larger than 6. Of course, this type of model can model everything in theory because it's unstructured. It can model any type of relationship, but that type of unstructured, lack of structure comes at the cost of an exponential explosion in the parameter space of the model. So we don't want this. As a recap from last week as well, the other alternative is to forget about the fact that this is a sequence prediction problem and just simply predict on each word in the input sequence independently to an output sequence, right? So predict for I independently, predict for fish independently, predict for off independently. Each one of these is now a 6-class prediction problem, right? And you have a string of 6-class prediction problems, which is now a tractable problem, and then you concatenate the predictions. So number of classes equals the number of part of speech tags, 6 in our example, solvable using multi-class prediction, but again, as we saw last week, it ignores context, so in particular, an independent classifier would classify fish as a noun because it's more often a noun than a verb, let's say in our training set, but in this particular context, between I and often, it is actually a verb. Right? So this model class is too simple. It imposes the most rigorous structure in some sense, right? Like everything's completely independent of everything else. So we talked last week about the first order hidden Markov model, which is a generative approach that generalizes Najve to model sequences, right? So the input sequence is X, the output sequence is Y. Then the first order hidden Markov model is fully defined by these probability functions. We have a probability that given that we're in state Y, so one of the part of speech tags, what are the probability that we'd observe some word? Given that the current state is Y, I, what is the probability that the next state, the next part of speech tag is Y plus 1? Then some special, and again, these are just special cases of the transition probability, but a special one for this, from the special start state, and a special one transitioning to the special end state. So, if you did the homework, these are things that you are hopefully intimately well aware of by now. And this is again the graphical model representation of a hidden Markov model, and many of these models can be represented in graphical models form. And the basic idea is that the arrows of the graphical model corresponds to exactly define the structure of the probability distribution. Recall that the fully sort of naive, unstructured setting will model all possible XY pairs. And this structural assumption, these arrows say that the actual probability factorizes multiplicatively into these little components. And the key thing that makes HMMs tractable is that these components are replicated, repeatedly applied as you go along the chain. So therefore the model complexity does not blow up with respect to the length of the inputs and output sequences. Any questions on this? Should be pretty clear. Okay, and we'll be using a lot of matrix notation in this lecture just because it's very convenient. So I'm going to go over this slide perhaps painfully slowly, just so we're all on the same page, because I'll be using matrix notation for the rest of the lecture. So recall that this is the HMM. So the conditional field will use a very similar notation for this lecture. So recall that the joint probability in the HMM is factorizing to the probability of the last state in the last output state transition to n, optional in many cases, times for each token in the sequence, the probability of the jth output token in producing the jth input token times the transition probability of the j minus 1 output token transitioning to the jth output token. And in the matrix form, this corresponds to two matrices of parameters, an A matrix, which is called the transition matrix, and an O matrix, which is called the emission matrix, also known as the observation matrix. And every entry in this matrix basically corresponds to one of these probabilities. You can think of these probabilities as probability tables, two-dimensional probability tables, right? And in which case, these matrices basically correspond to basically a matrix form of that two-dimensional table, right? So entry, and again, I guess there was some confusion about what is the semantic of the row versus the column. It does not matter so long as you are consistent within your own implementation. What is is the first index the row or the column row, the previous or the former? It doesn't matter. Yeah.
So it should be switched here, right?
It should be switched.
Because the O and the A are not consistent.
I'm sorry.
The A and the O are not consistent, right? So it should be switched just to double check.
J minus 1 to J.
The first index should be the conditioning and the second one, or the other way around, but they're both different.
You mean I switched the order?
Yeah, right.
Well, if you look at index, so like.
Okay, so this O corresponds to this P, and this A corresponds to this P.
Yeah, sure, but
No, not
now
that.
just because of consistency, I'm just like trying to see if
I
A
don't.
and O have the different formats, so I both them have to be switched, right?
I'm not understanding your question.
So I think
It
it's.
doesn't matter too much, but
These are entries of the matrix. It's not matrix multiplication. These are entries.
yeah, I know. But
Real.
the first entry should be like conditioning, and the second one should be the variable, right? Like for
the first entry should be conditioning.
Yeah,
So-
the variable you condition on.
Either, you could do it either way. This is one is just the transpose of the other.
But I think he's saying that it's inconsistent, because there, the first entry is what you're conditioning on for the A, the second entry, or the first entry is the output, the variable.
The
second
first
is what
entry,
you're
the first
conditioning
entry is what you, the
Yeah.
second entry is what you transition from. The first entry is what is your current state.
Yeah, that's
Yeah, but then the O
inconsistent.
doesn't fit. I'm
It
just-
should be the other way around.
Oh,
I'm
with
saying the A
O,
is
the
not
first
consistent.
entry, with O,
Should be
the
the
J
X.
corresponds to the current state, and the X corresponds to the emission of the current state. I don't see why it's inconsistent. So this J,
It's fine.
Yeah, it just depends on how you like it.
Yeah, but the O is fine.
I see, you think that this actually corresponds to P of
My
J minus
hypothesis
1
is-
could give him P of
If
J.
you have
Okay.
a consistency for A, then it doesn't
I'm
matter.
defining this as this.
Okay.
You can
no.
define it the reverse way, it's the transpose of this. As long as you are consistent, it's fine.
Yeah, forget it. It's fine.
Okay,
So-
I'm literally defining this probability table as this matrix. Yeah. So okay, this it.
Yeah, sorry, I'm not trying to mess this up. It's fine.
This is an important point because I hope that everyone, after they've done the homework, is just comfortable regardless of how the notation is, as long as they know that they need to maintain consistency within their implementation. Because when you look at implementations that people have in the wild, they'll define it either way, but as long as they're internally consistent within their implementation, it's totally fine. So my definition for this lecture is for the A matrix, the first entry is its current state, and the second entry index is the previous state. And then for the O matrix, the first entry is the current state, and the second entry is the emission of the word. Okay, great. Of course, we could use in lecture we could do something like this too. It's just the notation would just blow up, so I didn't want to do that for this lecture. Okay, just to recap our first order sequence models. So you're able to, so it's something that sits between general multiclass, which very intractable. One computes a unique score for each entire sequence, and between independent multiclass, which makes very strong independence assumptions. So first order model sort of sits between. It's a scoring function per pair of tokens and per emission probability. So it's somehow a sweet spot between fully general and fully independent multiclass. So just to comment on the relationship between naive Bayes and HMMs, because this relationship is analogous for logistic regression and conditional random fields. Recall that this is the sort of probability assumption of naive Bayes, which is not a sequential model, because it's just a single Y. It could be multiclass. Y could be multiclass, but it's just a single Y. It's not a sequence of Y's. And then here's the relationship between naive Bayes and Markov models. And the key assumption, that sort of carries over from the two, is sort of this naive generative independence assumption on the axis given the Y. Right? So you could think of HMMs as a first order sequential variant of naive Bayes.
Is there supposed to be an I in the last? They're both J.
Oh, I'm sorry, this should be a J.
Yeah.
Okay, now just another viewpoint. HMMs and naive Bayes are generative models, which means they model the entire joint distribution of input-output pairs, right? And one reason, and given certain independence assumptions, such as the naive Bayes independence assumptions built into both naive Bayes and the hidden Markov models, they're easy to train. You just they're compact, they're easy to train. You just do counting from the training set, frequency counts, sometimes regularized with pseudo counts. Actually, often regularized with pseudo counts. Right. And then you train by taking some training set Now the subscript is indexes over training examples, and superscripts I'll use to index over tokens within a sequence. Okay. So given a training set of training sets, you find the parameterization, which is often in machine learning terminology, like all the parameters of your models is something just referred to as capital theta. This is very common in machine learning terminology. So you can think of this as the A and the O matrix. Right? So this is maximal likelihood training, and if the data was sampled independently from the true distribution, the test distribution, then we want to model this probability sort of in a multiplicative way. Right? The key challenge, the key difficulty with using HMMs and naive Bayes for the standard prediction task is that in the standard prediction task, our goal is, given an X, predict the best Y, which if you have a probabilistic model, is given an X, predict the Y that has the highest probability. Right? Okay, but we didn't train our model to maximize this. We trained the model to maximize this, right? And so there's a mismatch between the training goal and the prediction and the conventional prediction goal. Right? So maybe we should actually train a model to maximize this instead of this, right? Wouldn't it be great to actually make our training criterion maximize the conditional probability of the training set, condition on the X's in the training set, rather than the joint probability? Right. So it's weird, in some sense, if your goal is this is the only thing you can ever use your model for, right? Given an input sequence, predict an output sequence. Right? It's weird to define a model this way in order to train it like this, when in some sense, intuitively, we should be training a model that maximizes this goal, right? We should maximize the conditional likelihoods of our training set, condition of the X's in our training set. So if we still want to use a hidden Markov model, right, which actually defines a joint distribution, this actually becomes this, right? And this term becomes this, right? And this is actually a pretty complicated optimization model, right? Yeah, you break all the independent assumptions, come over, you can use count statistics, and it just becomes very messy. And both HMMs and naive Bayes suffer from this problem. Yeah.
That counting thing, does it actually maximize that?
This counting thing, it maximizes this, yes.
Oh.
Yeah. So for both naive Bayes and HMMs. Sorry.
Is it easy to see what?
Yeah. So if you go back to a lecture from last week, for like the first lecture on Tuesday, we talked about how for naive Bayes this is true, and then the second lecture I alluded to how for HMMs this is true. It is pretty easy to see. In practice, of course, with finite sample sizes, you do regularize with pseudo counts, but I'm not sure that. Okay, so this is hard. This is actually a hard optimization problem given the model structure of HMMs. It's not clean. It's messy, right? And so maybe the lesson to take from this is if you have a probabilistic model, if you define a probabilistic model of a certain form, you should maximize the likelihood of that model that you define on your training set, and not some other model. If you define a joint distribution, you should maximize, if you decide to model the joint distribution for whatever reason, maybe for the variety of reasons we talked about in the previous lecture, previous week, then you should train your model to maximize the joint probability over your training set. If you define a conditional model, like P of y given x as your model, and you don't care about the joint distribution, then you should maximize the likelihood of P of y given x on your training set. And that's what we'll be focused on for most of this week. Yeah.
Are there situations where those coincide, or is it just generally not going to happen?
What
Or
is
is
that?
maximizing the joint, maximizing the conditional argument being coincide, or is it just never reasons like that?
I don't know that. Okay. I mean, there's a degenerate case where x is always the same.
Yeah, I assume we could over
Yeah. Yes.
I think that's learned that P, that's a conditional probability, right? But why you said that's to maximize the joint distribution?
I'm sorry, could you just repeat what you said? I didn't follow.
Yeah,
what you said.
the count, right?
Yeah.
a conditional probability. Yeah, but why usually that formula is to maximize the joint?
Oh, because this thing is like, this thing decomposes multiplicatively into terms like this. So as you saw in the previous week, if you just reparameterize this into the log likelihood, it's a bunch of sums, right? And then you could show that this is the optimal solution. If you want to this is your model and you want to maximize this, when this is your model, then you have to divide by this, right? And this makes it very messy. So the lesson, to the high-level lesson is, whatever model you define, you should maximize the likelihood of that model on your training set. If you define a joint distribution, which HMMs and Najve Bayes define, you should maximize the likelihood of that joint distribution on your training set. If you recall from the first week or second week of lecture, we showed that minimizing log loss was equivalent to maximizing the conditional likelihood of logistic regression, right? Logistic regression, logistic regression defines a conditional probability of y given x, and maximizing the conditional likelihood of that probability distribution on your training set is equivalent to minimizing the log loss, right? We saw that, and so we'll see something very similar in this lecture. So generative models model the joint distribution, use Bayes rules to predict the most frequent prediction task. One benefit is they could generate new samples. They could also sort of fill in missing values. Right? Examples include Markov models and Najve Bayes. Discriminative models directly model the conditional distributions. They cannot model the joint distribution. They only model the conditional distribution. But now whatever you learn is used to directly make predictions on the most common prediction task. And these include conditional random fields and logistic regression. And both models are trained via maximum likelihood, right? If you define a generative model, you maximize this probability on your training set. If you define a conditional model, you maximize this probability on the training set. For logistic regression, that's equivalent to minimizing the log loss, mathematically. So here's a first try. This is sort of the unstructured version of the model, right? Similar to what we saw last Tuesday with an unstructured joint model. Here's an unstructured conditional model, where we just sort of have this table that we model even for just classifying a single y, a binary y, sort of given two x's, sort of all possibilities, what is the probability of y given these two x's, right? And if you do define your probability, your y given x in this way, you can in fact train by discounting. The drawback, of course, is that this type of unstructured model has complexity that is exponential in the length of x, right? For in the case where where there's 2x and each x is a binary value, then there's 4 possibilities, and that sort of scales with the polynomial is right scales with the length of the number of x's. So we need to assume something, right? We can't just do this. We need to assume some additional structure. What should we assume? I would normally ask the class, but the answer is something that I already repeated about 5 times in the first 10 minutes. So the answer is logistic regression, which is also known as a log linear model. So recall from I think it was either the first or second week of class. This is the logistic regression for linear binary classification, right? So the idea is you have some vector of x's, and then or multi-class classification in this case, and then you have a weight vector per class, and then the probability of that y given that x is proportional to e to this linear scoring function divided by the sum of all the scores. Right? It's often called log linear because it's linear within the exponent. So this is the most common discriminative probabilistic model, logistic regression model. Prediction, pick the y that maximizes the conditional probability of y given some input x. Training, train the parameters of this model, which is basically all the w's and the b's, the biases, to maximize the conditional likelihood of the training data. Note that now they match, right? What your training goal matches your prediction goal. So when you tune this model on a training set, you can be confident this model is being tuned to get good performance on your prediction task that you care about. assuming that this is the only prediction task that you turn. So let's do a comparison of naive Bayes versus logistic regression, right? Strong independent assumption, super easy to train, mismatch, prediction, looks kind of like this. Regression looks kind of like this. Log linear assumption. So now the reason why this has fewer parameters than that unstructured conditional model is that we're making a linear assumption. Right. Harder to train. You have to use gradient descent. These days, not too hard, but still harder. It matches prediction. Naive Bayes, if you think about the parameter, number of parameters between naive Bayes versus logistic regression, if you look at the first term, right, it has L parameters, one for each possible Y. There's L possible Ys, right? And logistic regression has L parameters for each of the bias terms, right? Naive Bayes has L times D parameters for this probability table, P of X given Y. Right? Logistic regression has also L times D parameters for a W for a W vector for each Y. They have the same number of parameters. In this very real sense, both logistic regression and naive Bayes have the same model complexity. So another way of phrasing it is that both models have the same capacity. On the one hand, naive Bayes spends a lot of that capacity on modeling P of X because it models the joint distribution, right? Logistic regression spends all of that capacity modeling P of Y given X, right? So given that your model is an imperfect model of what you're trying to capture, of the phenomena you're trying to capture, given you have finite training data, if this is your goal, then logistic regression spends more of all of the model capacity trying to fit that goal, whereas naive Bayes tries to do more things, which means that it does less well on this goal in general. No model is perfect. Naive Bayes are trade-off between this and this. Trade-off between estimating everything, which includes this and this. Right? In logistic regression, given the same number of parameters, we'll try to fit this as well as possible. And the same intuition, of course, generalizes to H of n versus conditional random fields. Okay, so that is the somewhat long-winded recap, but now we're going to talk about conditional random fields. Yeah?
Sorry, one question. In the formula, why are we summing over WKs? I didn't understand that.
This one?
Yeah, we're in the denominator, we have WKs, like different WKs.
Oh, I'm sorry, this should be, sorry, that's a typo. It should be,
We're summing over K and we're enumerating W.
so K goes from 1 to capital L.
So with L different weight vectors.
Yes. So imagine in the binary case, it's just 2.
Oh, because we have L classes. Okay.
Yeah.
Yeah, I get it. Yeah.
And that's actually a typo.
Okay.
Okay, so here's the definition of conditional random fields. I'll just walk you guys through it. So recall that X is an input sequence and Y is an output sequence. The probability of Y given X is defined by this term. So it has the exact same form as logistic regression. It's just that the scoring rule on the inside is not just a simple, at least not in this version, a simple dot product, right? So so basically we have the same number of parameters as hidden Markov models. We have this transition scoring rule and this observation scoring rule. And we're basically linear in the sum of the scores of transitions and observations. So what does this mean? If we have, well, actually I have an example in the next slide, so let me just go through the notation. We go through every token in this input in the sequence, and for any given Y, we compute the score of the transition from the previous token to the current token, compute the probability of the current token being associated with this word. Now, there's no independence or conditional probability. There's no independence assumption here. Everything's just summed together. Just like how logistic regression, everything's summed together Whereas naive Bayes made these generating assumptions. There are no generating assumptions here. Everything's just summed together, just like in logistic regression. And this term here is also known as the partition function, which is a term borrowed from physics, statistical mechanics. And the basic idea is the same. We take a summation over a bunch of scores, we add them up, we exponentiate it, and then we divide by the same scoring, exponentiated score row over all possible sequences. So the probability of this particular input sequence X generating any given output sequence Y is proportional to E to this scoring rule, which sums over the transitions, scoring scores, and the emission scores. And I have an operational example in the next slide. This is the complete notation. Yeah.
Why are we summing over the length of the sequence, J from 1 to M? So depending.
So recall that in hidden Markov models, you take a product over the sequence, right?
Yeah.
So if you sum over the length of the sequence inside the exponent, you're actually taking a product over the sequence. But we're not making any explicit independence or generative assumptions. It's just E to a linear scoring rule. Yeah.
So are the A and O here the L1-wise logs from the previous one, or are they the same as the previous one?
I'm sorry.
Are they the logs of the previous A's and O's? Like before we define the A and O.
Yeah.
So are these the logs of those, or the actual probabilities?
If you were to interpret these as probabilities, they would be the logs.
Of those probabilities.
Yeah, so I don't know how much, okay, so those of you who have done some extra work on logistic regression know that the coefficient of logistic regression, the W's, correspond to an increase in log odds as you increase the X input. You can think of this similarly as the increase in log odds of some sequence as you increase a certain transition. As you add a certain transition. Yeah. Yep.
So I've also, again, like implicit, as you said from this argument, that it splits into the product with an implicit assumption for independence between the transitions, right?
We have an independent assumption, but it's not a generative model.
Right. Yeah. Conditioned on the observation.
We assume that the scoring rule is independent. It factorizes pairwise, but it doesn't define a fully generative model. Yeah.
So if you wanted to be second order, it would be like 3 subscripted.
3 subscripts. Yep. And next lecture, we'll look at a more general formulation of CRFs, which will be able to include stuff like that. Yeah.
I still don't understand why you do the summation for these 2 different variables. Why you cycle the A and O?
So recall that, so there's some connection between this and HMMs, although, so recall that in HMMs, you take the product over every thing in the sequence, right?
Yeah.
So if we sum in the exponent, it's equal to taking the product of each of these, right? But we're not making any generative assumptions, but it has this, if you think about it that way, it has the same structure as an HMM, but it's not a generative model, it's a discriminative model. Yeah. So, E to the sum is equal to the product of E to the individuals.